Video number 2. Here we are. Let's go. Welcome back, folks. Section 5.2 is on perpendicular bisectors, for starters. Section 5.2 is called Use Perpendicular Bisectors, but they're a means to an end that comes later. They're part of a much bigger thing. So, first of all, if the name perpendicular bisector wasn't a big enough giveaway of what it actually is, imagine I have just some segment with some endpoints. Go ahead and pretend that line is straight. If I were to talk about the perpendicular bisector of this segment, well, sorry, I have to change colors here. That would be one that does two things to it. One is that it cuts it in half, such that these two sides are now congruent to each other, and also it's perpendicular to it. So when it intersects, it's going to form a right angle. Bam, perpendicular bisector. I don't think that was too hard. So there's a theorem that comes off of that, of course. There's always theorems that come off of everything. So the perpendicular bisector theorem, which don't worry about remembering how to do this in a proof or anything, or remembering what it's called, but the perpendicular bisector theorem says if a point is on a segment's perpendicular bisector, it's going to be equidistant from the segment's endpoints. So take a look at this diagram to the right, which spells buns, for no reason really. It's going to be the case that if I have a point on there, like point B, if I were to measure the distance from B to U, and B to S, they're going to be exactly the same, which means they're going to be congruent. So, as far as actually showing why this is, it says why, and then a big line like we got to fill something in there. We'll think about this. What we should look at right away here is see two triangles. So if I want to show that two segments are the same, if I'm trying to show that two segments are congruent, and I got some triangles going on, you should probably be thinking, show triangle congruence, A, and then B, show CPCTC. Alright, fine. So, here we have a reflexive property. Tell me that Bn is congruent to itself. I have right angles here. This is also right, so I have two right angles congruent to each other because of the right angle theorem. And then I have Un congruent to Ns, and that's kind of given by the fact that the red line is a perpendicular bisector. So what I have is this this whole left guy congruent to this right guy because of, ooh, that was bad. You see what I'm getting at here. Congruent to each other because of S, A, S. So, I could then show that these two sides are congruent to each other, BU and BS, because of CPCTC, and therefore, B is congruent, or sorry, not congruent, B is equidistant from U and S. So what did we show? We showed triangle congruence via SAS, and then CPCTC. Cool. So, the converse to this. Well, look back at the original theorem here. It's an if-then statement, which means if we want to take the converse of it, we just flip the beginning part and the end part. So if I had if P then Q, now it's if Q then P. So, here we go. If I want to flip this, if a point is equidistant, ooh, this handwriting, from endpoints, then it is on the perpendicular bisector. Ah, beautiful. So, with that being said, let's look at the bottom part. Does point A lie on segment ES? Why or why not? Does point A lie on it? Okay. Well, I see here that it looks like definitely point S is. And if you were to go with the logic like, well, if I extend this, it kind of looks like point A is on, or maybe it doesn't. Well, you're wrong. Don't do that. Be more analytical than that. We shouldn't be judging it based. You should know by now that because it looks like it is never really a good answer in geometry. What we should be doing is analyzing this and drawing conclusions based on some kind of theorems. So clearly we can see point S is on it, and that makes sense because S is equidistant from B and N. Also, this triangle spells beans. Ha ha ha. Well, let's look at what we have going on with point A. A is equidistant from B and N as well. It's both 27. So what that should tell me that is that because the converse, if a point is equidistant from endpoints, then it's going to be on the perpendicular bisector of that segment. A is equidistant from B and N, therefore it's on the perpendicular bisector of BN. Yes, because this, the converse theorem. Neat. Hey, speaking of neat, we got a kite going on here with a pretty picture and everything. What you should be saying is in your head at least, I think I know how to solve this, or I want to give it a shot before I watch Mr. Murphy do it. So if that's the case, just pause the video and have at it. I'm going to give you a couple seconds for, first of all, me to figure it out, and second of all, for you to pause the video and try it yourself. Alright, that's enough time, I think. Let's see. We want to say that given KT is a perpendicular bisector of EI, label all congruent segments. Okay. Well, E is congruent to E. Or, sorry, 8 is congruent to 8, last I checked. What else do we know? That would imply that, well, we already know, sorry, that KT is a perpendicular bisector of IE. So that would imply that these two parts are congruent, because IE is being bisected. We also know this is right. We weren't asked about that, but okay. And then it looks like T is also on the perpendicular bisector of IE, so I guess that means ET and IT are congruent as well. T is on the perpendicular bisector of IE, so ET and IE are congruent. Fair enough. We want to find the perimeter of triangle ITE after that, which is, let me highlight that real quick, this guy. And we could do that by, first of all, solving for whatever x is, which isn't too hard, right? We already have that IT, which is 6x minus 5, is congruent to ET, which measures 4x plus 1. So if I want to solve for x, fine. Subtract 4x from each side, add 5 to each side, and that gets me x equals 3. If I plug that back in here, that's 6 times 3 minus 15. Alright, so that's 18 minus 5, which is 13. Okay. Just to double check, like, this should also be 13 because it's congruent, but if I plug 3 in, it should still work, right? 4 times 3 is 12, plus 1 is 13, so that checks out. Great. Because IE was perpendicularly bisected, that would imply that SE is also 7. So the perimeter here, perimeter of triangle ITE, notice the subscript I'm using, it's going to be IE, which is 7 plus 7, plus ET, the second side, plus IT, third side. That gives me 7 plus 7 plus 13 plus 13. I could group this in a convenient way to get 40. Any units? Nope, so just 40. 40 bananas if you want. Okay, some vocab and some pictures. Nice. So, here's what I'm going to be throwing around for the rest of the video, and probably for the rest of the chapter, which is concurrent and concurrency. So, when three more figures intersect at a point, they are called concurrent, and that point where they intersect is called a point of concurrency. So, let's talk about our first point of concurrency, which is called the circumcenter of a triangle. This is a pretty big deal. This is going to be where all the perpendicular bisectors of a triangle meet. And there's going to be some very interesting properties about the circumcenter as a result of some of the theorems that we just looked at. So, something of note is that it's equidistant from each vertex in the triangle. So here, if I say, in this picture to the right, if this now red point is the circumcenter of a triangle, it's going to be equidistant from C and I and R. I should have labeled this thing. Let's go with C for I can't do that, there's already a C there. Crap. Poor planning, Murphy, poor planning. Let's call it O for oops. So, OC is congruent to OI, which is congruent to OR, because O is equidistant from the vertices of the triangle. Again, that's if O is the circumcenter. So we can actually justify why this is. Take a look at the triangle on the bottom. It's going to be the case that, choosing colors, YZ is being intercepted by this orange line that we're being told is a perpendicular bisector, this one in particular. So what that means is, this part's going to be congruent to this one, we have a right angle there, that's cool. But more importantly, C, which is a point that's on the perpendicular bisector, is going to be equidistant from the endpoints of Y and Z, which means this, let me just pick a different color for this, YC and CZ are going to be congruent to each other. So let me get rid of some of this other stuff in here. And again, that's because C is on the perpendicular bisector of YZ. So, well, guess what? I could look at any of the other perpendicular bisectors and say the same thing. Like if I want to look at this vertical one over here, I could say that because the segment YX is being perpendicularly bisected, and C is on that perpendicular bisector too, then it is also equidistant from y and x. So I guess these sides are congruent to each other. Basically what we have here, if we just apply the perpendicular bisector theorem 2 or 3 times, is that C is equidistant from all the all the vertices of the triangle. So this type of triangle that we have here is inside of something called a circumscribed circle. Whoops. As we can kind of see, which makes sense. Pretty much the definition of a circle is that it's the set of all points that are equidistant from the center. So C, which is the circumcenter, and also the center of the circumscribed circle. Oh my gosh, these tongue twisters. Yeah, it's equidistant from y and z and x, which are on the circle, and C is equidistant from pretty much every point that's on the circle. That's kind of what it means to be a radius of the circle. So my drawings are becoming crazy now. Let's take a look at this a little bit more on Geometry Sketchpad, which is a thing on your iPads that you can play around with, and just kind of when you're done with this video. So 1 second while I rearrange my gear here. So, check it out, folks. I'm actually holding up my iPad to my laptop screen. Believe it or not, this is the best way to do this that I can think of. And I'm showing you the GSP file that you have all the ability to play with also. That's in eBackpack right now, or if you're watching this in the future, maybe Canvas, who knows. And it's called 5.2 circumcenter.gsp. So, here we have a demonstration of all these red lines, which are perpendicular bisectors. We can see so because they're perpendicular. This one's perpendicular to JK, and also it bisects it. We can see that because of the congruence marks. And they're all meeting at the circumcenter, which happens to be the center of this circumscribed circle. And also it's the thing that's equidistant from J and I and K, because the distance from the point to J and I and K is equal to whatever the radius of the circle is. So as far as like playing around with stuff, maybe we wouldn't have to play too long until we notice something strange, which is if I start dragging the stuff around, like, whoa, this is weird. The circumcenter of a triangle is outside of the triangle. How can a center part of a triangle be not even inside of it? So, it's still the case, like, everything makes sense still. Everything we said is true, which is that this point is equidistant from J and I and K. It's still a distance of R, the radius away. But as far as like when it's inside and when it's outside and even when it's on it, well, that has to do with what type of triangle that we're looking at. So notice here, like, we can actually see the triangle measures. They're all acute right now. This is an acute triangle. But if I start fiddling with one of the vertices for a bit, should I mess with that one? Let's put that one there. This is good. Let's keep going. If I make it a right triangle, which, I mean, I'm pretty close here. Cut me a break. 90.08 degrees. We can see that it actually starts to be not in the triangle, not outside, but on the triangle, on the midpoint of the hypotenuse, actually. And if I were to go any further than that, if I made this angle obtuse, which it now is, then it's outside of the triangle. So, that being said, here's this. Basically saying that the location of the circumcenter is going to depend on the type of triangle that we have. So if it's an acute triangle, then P is going to be inside of it. If it's a right triangle, then it's going to be on it. More specifically, it's going to be on the midpoint of that hypotenuse. Midpoint of hypotenuse. And if it's an obtuse triangle, then P, the circumcenter, is going to be outside of the triangle. So, here's a problem. Finally, some math. Yay, with some numbers. So let's take in all this information here. G is the circumcenter. The blue segments are perpendicular bisectors, and the red segments have endpoints on the vertices. Okay, so this looks like just a pile of garbage that we have going on here. But let's actually try to make some sense of it. So let's start off with the fact that the red segments are segments that go from the circumcenter, the big deal here in the middle, G, to the endpoints on the vertices, or sorry, to the vertices of the triangle. Alright, so that means that they're all going to be congruent to each other. We have that going on for us so far. The blue segments are perpendicular bisectors, which means everywhere here we have right angles, right angle, right angle, right angle, and also, because of the bisected part of perpendicular bisector, we know we're going to have some congruent segments as well. So in setting all these things equal to each other, or establishing right triangles or whatever, this is going to be enough to actually find out BG and BA and AF as we're being asked. Let's go with orange, yeah. So, for BG, we don't we don't have many clues to figure out what BG is congruent to, or sorry, what it's equal to, except for the fact that it's congruent to the other two red segments. GA, for example, is 9, so I guess that means BG is also 9. Because because G is the same distance away from each of the vertices. Fine. BA, okay, so BA is this guy, which has been perpendicularly bisected into BD and DA, which are congruent to each other. Cool, so I guess that means DA is 6. Cool, I guess that means BA, according to the segment addition postulate, is 6 plus 6, aka 12. Neat. So AF, okay. This is where it actually gets a little bit more interesting. We don't have much to go with AF down here in green. Let's go with in this triangle, other than the fact that apparently it's a right triangle with a leg length of 3 and a hypotenuse of 9. So let's call it AFX for a second to make this easier. That's really all we need, really, because if we have a right triangle and we know 2 of the sides, we can find the third side with the Pythagorean theorem. So I'm going to set that up. 3, whoops, that was bad. 3 squared plus x squared equals 9 squared. So remember, the thing that we're solving for isn't always the c. Whoops. In this case, we are solving for the leg, and we know the hypotenuse to be 81. So x squared is going to be, let's see, 81 minus 9 is 72. So I guess x is equal to the square root of 72. Which, if you know anything about reducing radicals, which we're going to do later, that's 36 times 2, so it's 6 root 2. That's the stellar answer, but I'm fine with root 72 as the final answer. So that wraps up this video. More to come in the future. Thanks for watching.